Hello everyone, welcome to Excel Maths. So today we are going to be discussing question number 6 from June 23, real paper, paper 3 mechanics. So this is the last question. Rest very quickly. We have covered everything from 1 to 5 in previous videos in the same playlist. I have tagged them in. Okay, let's get started with the same. So we have a rod AB which has mass M and the length is 2A. That's fine. Let's highlight the information. So mass is M and length is 2A. The rod has its end A on the rough horizontal ground. So this is rough and that one is smooth. B is smooth. Nice. The rod makes an angle theta that we can see over here. The rod is resting. The rod is at rest in limiting equilibrium. Limiting equilibrium means the frictional force is maximum here, right? Okay. So the frictional force has reached its maximum limit, we can say, or F max is acting over here. Now, the first thing we have to find out, state the direction left or right on the figure 3 above of the frictional force acting on a rod A. Give the reason for your answer. Okay, let's understand. Before I say anything, you're going to be think about it. I'll be showing you a video over here, okay, as you can see. So I just tried, demonstrating the same thing. So it's a pencil and again the resting on the setup, which has the walls are 90 degree as 90 degrees as the diagram. Now, if you see, when I'm, pulling the paper towards me, the object falls down. I just want you to see again. So the direction of the force is like this way. Let's see. Direction of the force is this way, and so initially when the object was not falling, even I'm pulling it, pulling the paper, it is not falling. That means friction was there. The moment it falls down, that means my force is greater than friction. So what the question is asking? The question is asking that the rod is resting. The rod is at rest. Though it's a limiting equilibrium, but it's at rest. So if it is at rest, that means friction is going to be acting and it will try stopping the object. And what the direction of the friction will be? The direction of the friction will be towards the wall. So they are saying right or left. We can say right. So it would be the right direction, right? And we have to give a reason for your answer. So just to oppose the motion, what can we say? Just to oppose the motion, friction is acting towards the right side. Correct? Now, the next thing is the magnitude of the normal reaction of the wall on rod at B is S. So this is the point B and that is the wall, if you can see, and we have a magnitude of normal reaction, that is S. In an initial model, the rod is modeled as being uniform. What do we mean by uniform? Uniform means weight is going to be acting at the midpoint. Weight at midpoint. Okay. So we've got two keywords. The first thing was limiting equilibrium. That means friction is maximum there. And the uniform means weight at midpoint. Okay. Now after this, we should really understand very well what all the forces are acting over here. So for that, we're going to be having a quick go through of some visualization. I'll be showing you my screen. Just give me a sec. Okay. Yeah. So over here we can see the plane, exactly the smooth wall and the rough ground. Now we have a beam over there. We'll see the forces. The first thing is we understand that this is uniform and weight. Let's talk about the first force, that is weight. So the weight is acting downwards and weight is mg. Why? Because the mass was m, capital M. This is the first force. this weight, because the object is not moving, right? It's not moving, the rod is not moving, it's at rest. That means it's going to be balanced by some force. So the same, but exactly same, but in opposite direction. So we are going to be drawing the next force, that is going to be the reaction force, and this reaction force is actually balancing the weight. Every time normal reaction balances the weight, right? Now the second force, because we have seen the A part was talking about the friction. So the friction right at the foot of the beam or the rod, this is friction. This friction is going to be balanced by the normal reaction of wall, right? The angle we have over here between the horizontal ground and the beam is theta, and the same angle will be there between the rod and S. Okay, so these are the four forces. Whenever you get this setup, you have to draw these four forces. Just write down like your key point, that whenever we're going to be getting this particular scenario, we have these four forces. Okay, now let's start resolving the forces, finding out the components. So for component, let's start with mg. So if that is theta, this will be theta, and the first force comes mg cos theta. You would be understanding that the cos goes to the adjacent one, and the other force is mg sin theta, right? So the solid is the real weight or maybe the force acting downwards, and the dotted lines or the dotted arrows are actually the component of the forces. And just the next note, I would say, whenever you whenever you draw the component of the forces, make sure the sine and cos should have 90 degree and 90 degrees angle between them. And the second thing, your real force should come in between. It shouldn't be going like out of these two forces. I will show you the condition. Now let's go to the next force. The mg was balanced by r, so we are going to be resolving r. So this is r cos theta, and the other one is r sin theta. Again, r cos theta and r sin theta are making 90 degrees, and r is in between r cos theta and r sin theta. Let's write the components of frictional force, F. So this would be F cos theta, and downwards we're going to be having F sin theta. The last one is S. So here we're going to be having S cos theta, and perpendicular to the rod, we're going to be having S sin theta. Hope all these components and all the forces are making sense. This is the most important skill you should have. Like, you should be very clear with these things. So every time whenever this setup comes, you have four forces. Make sure you have four forces, and there is a reason for those four forces, right? Your weight is going to be balanced by normal reaction, which is normal reaction to the ground, horizontal plane, and your frictional force is going to be balanced by normal reaction of the wall, right? We have two normal reactions, normal reaction of the ground and the normal reaction of the wall. Now these four forces, you just have to write the components of the forces. Okay, now I'm going to be taking the screenshot of this, give me a sec, and using it over there. Okay, so it's here. Perfect. Let me arrange it. It's here, right? Okay, now let's move to the next part, B part. What it says, by taking the moment about A. A is this point over here. We have A over here, and we have to, by taking moments about A, show that S is half mg cot theta. Okay, so moment is nothing but force times perpendicular distance. So let's take the moment about A. So we are going to be taking the moments about A. Okay, so A is this point. Whatever you would be knowing, when we talk about moments, just make sure whatever the forces are acting at point A are going to be 0, because perpendicular distance is 0. excuse me, the force is there. The force is there, but the perpendicular distance is 0. So overall, the moment at a particular point is 0. So about A, whatever the force is, like r cos theta, r sin theta, whatever the forces we have, the moment will be 0. Now, what forces are going to be really active for this thing? So I think we're going to be having mg cos theta active and s sin theta active. So let's do that. So can we say that what is moment? Moment is force times perpendicular distance. Okay, so we have to check whether what is the direction of this force is. So mg cos theta, it's going clockwise. So we can write mg cos theta times what is the distance, because it's a weight and the beam was uniform, rod was uniform, so we're going to be getting this distance to be a. We have written a. That is going to be equal to, this is opposite, anti-clockwise, so that is going to be s sin theta times 2a. A to a cancelled, so we can say mg cos theta is equal to 2s sin theta. I need to check what exactly we have to prove. Okay, so we have to make s the subject. So s is going to be mg cos theta over 2 sin theta. That is nothing but a half of mg cot theta, right? And I think this is what we need to prove. So half of mg cot theta. It's done. And we have got our 3 marks. Very well done. Great job. Okay, the next question we have, next part we have over here for 5 marks, the coefficient of friction. Okay, the coefficient of friction between the rod and the ground is mu. Okay, given that tan theta is 3/4, find the value of mu. Okay, to solve C part, I would say, I'm going to be writing C over here. We have to find out the value of mu. So we know F max is nothing but mu r, right? Now F max is the friction, like this particular friction is F max, and I'm writing F max because it was the limiting equilibrium there. So F max is equal to mu r. If somehow we try finding out F max and r, so mu is nothing but the, you just need to divide and you're going to be getting that. Okay, this force is going to be balanced by S. So can we say F, because F max is equal to, as F max is balanced by S, that means it is equal to S. So let's substitute over there. So S is equal to mu r, or instead of writing r, your r is balanced by mg. So we can say mu times mg. Correct? Mu times mg. Okay, S we found that was half mg cot theta, that is equal to mu mg. So mg to mg cancelled. We are having the value of mu to be half of cot theta. That means half of tan theta is 3/4, so cot theta would be 4/3. That gives us 2/3, or you can say 0.666 recurring, so 0.67 is our answer for mu, and it gives us 5 marks. It was easy, no? Yeah, but it was not a lot of working, but definitely the decision in the brain. That gives you 5 marks here. Now the D part. For the D part, find in terms of M and G the magnitude of the resultant force acting on a rod at A. We have to find out the magnitude of the resultant force acting on the rod at A. Okay, so that was there. We did B part. Let me just move it a bit so that I can get some space. This is C part. I'm going to be writing D part here. We will be doing D part here. Okay, let's go through the question again. What is it asking us? It is, I think, asking about the resultant force at A. So where A is this particular point. So for this particular point, if you have to find out the resultant force, let's focus on these two forces, R and F max. So let me draw. This is R and that is your F max. Actually, F max is nothing but mu R and R is mg and M like capital M, okay? Let me write it back. Okay, capital mg. Mu was 2/3 mg. Okay, so we have to find out the resultant. So the resultant force will be square root of R squared plus F max squared. Correct? Now R is mg. Let's substitute the values. We're going to be getting mg squared plus 2/3 mg squared. That gives us, can we take mg outside? It will give us 1 plus 4/9. That will give us mg square root of 13/9, or we can say 1/3 of mg. It's not looking nice. Let me write it back. It would be, root 13/3 mg. Is it looking better? Yeah. So this is what the answer for D part is. Okay. Let me explain back. If you feel like I'm just, self-teaching myself. So we have D part where we have M and G. Like in terms of mg, we have to find out the magnitude of the resultant force acting on the rod A. So we have taken the point A and we have taken all the solid forces. The solid force R and F max. R was mg, F max was mu R. Just substituting the values and we've got the resultant force. Now the last part, what it says, the last part over here is asking us, let's see. Okay, so the D part, it is asking us that in a new model, the rod is modeled as being non-uniform. It is non-uniform with a center of mass closer to B. So we have, let me show you. Say for example, this is a point, maybe this is a point that is a center of mass, like new center of mass where weight would be shifting there, like this is mg, right? Now new center of mass closer to B, we have to find out the value of S. I mean, in a model, a new value of S is calculated using this new model. With tan theta, the angle is the same, theta is the same, that is not changing. Only the thing which is changing is the position of center of mass, like it's non-uniform, so it's shifted towards B. Now state whether this new value of S is larger, smaller, or equal to the value of S, value that S would take using the initial model. Give the reason for your answer. Okay. There could be many ways to solve this as well, I feel. First thing, we can go with moment. So initial moment was initial, because S is equal to frictional force. S is equal to F max. F max is equal to mu R and R is equal to mg. So mu mg. So basically S depends upon mg. Now if your mg is shifted, so when we talk about the component, like when we talk about the moment about A, because initially mg was at midpoint, now it is shifted at this point, so the moment about A would be larger because the moment about A is larger, it's increasing, then S will also increase. It will change the value of S. Does that make sense? I mean, because everything is same, when we look over here, our value will change. Say for example, initially it was A, now it is say for example 3A. I mean 3A, it can't be A because it's total A. Say for example, it's what can we say? Can we say 1.5A? So 3 halves of A. If I add 3 halves of A, what the value of S you're going to be getting? Instead of A, you will be getting like divided by, no, 3 halves. So 3 halves, like 3, so that would go 3/4 of mg cot theta. So 3/4 of mg cot theta. Initially it was coming half mg, now it is coming 3/4. Does that make sense? Is it clear or confusing? What I'm doing, let me try back once more. So what I'm doing, first method we are using, second method also I'll show you. Let's quickly discuss the first method, because our center of mass is changed, the position is changed closer to B. Now say for example it was 0.5 and that was A. So the total distance from A to this new point is maybe 3 halves of A. Correct? So instead of writing A, we're going to be writing 3 halves. So we're going to be writing 3 halves here. So we will be having 3 halves. So the answer will go 3/4. Isn't it? Like 3/4 is greater than half. Everything will be same. It will be 3/4 of mg cot theta. So your value increased because your moment distance is increasing. So this is, but this is for understanding. You have not to really show all those things there because it's for just 1 mark. It's just for 1 mark. So you are going to be saying as distance, the perpendicular distance, obviously, as the perpendicular distance between center of mass and A is increasing, S will increase as the moment about A will increase. And you have seen S depends upon moment about A. Now the practical method. Let me show you the practical method. Say for example, this is a room. I mean, this is a room and I'm drawing a door here. Say for example, this is an open door. Does that make sense? It's a room. Huh? So this is the door and this thing is a door. This is a door. Okay. Now it's a knob. What you have to do, you have to open or close the door just by applying some force from close to the knob, like from this point. At this point you have to push or pull, and the second, these are the hinges, right? These are the hinges, like where the door is attached to the wall. So if you try pushing the door from this point, I'm saying this is point P and that is point Q, close to the knob and close to the hinge. If you push the door close to the hinge, it will take more force as compared to Q. So your S will increase because this time your center of mass is shifted towards B. Hope it makes sense. Thank you so much, and obviously your comments are valuable. I mean, I don't know how long it takes for me to really fix all the things and make my imagination coming to the screen. It really takes time. So if things are actually making some sense and making your life easier, a thumbs up and the comments, that will help us do some quality work, isn't it? Okay, bye bye, take care, see you soon, bye.